Okay, so we have 5 chapters today. So tool use and agents, uh, LLMs for synthetic data, representation engineering, mechanistic interpretability, and the linear representation hypothesis. Okay, so starting with tool use and agents, which is the most, in my opinion, the most practical and useful for regular people who aren't researchers. So an agent, an LLM can be part of an agent that can extract um, information or take actions via different tools. I um, there, I think in an earlier chapter this may have been mentioned, um, but the agent may be able to. Well, LLMs just output text, right? So we can prompt an LLM or train an LLM to get it to output a certain command that can either um, be used to retrieve information or be used to take an external action. And so that um, can be integrated into a whole AI agent system. And we already saw that with retrieval augmented generation to some extent. There's also a lot of other things that we can do. So yeah, we can call external APIs and execute code and access proprietary information, etc. There's a few different approaches that have been tried. Um, modular reasoning, knowledge, and language, or MRKL, is an architecture that has a collection of expert modules that specialize in different things. Um, and the LLM is general purpose, and it basically upon a request to the general purpose LLM, it um, chooses which expert to query, and it gets relevant information from that expert, and then integrates that expert's response into its own response. And so they can be uh, each expert module can be a neural network on its own, um, or it can be some other um, entity or some other module like a calculator or weather API, etc. Um, and so the LLM just is kind of like the leader and calls each one. There's also different architectures that um, fine tune an LLM to call different tools, and ChatGPT and OpenAI have their own um, way of doing this, basically allowing an LLM to use different tools. And there's Hugging GPT from Hugging Face um, for task planning, selecting the expert model, and executing tasks and generating responses. And so here's some pseudocode to generally get an idea of how this works. There's also somebody made an API bank benchmark, which basically detects how good an LLM agent or an AI agent system makes use of different APIs and experts and is able to call those things. And there's like probably more than 100 different APIs and workflows and dialogues and tools that the benchmark can test an LLM system on. And there's so many different tools and that an agent can use that they even have an API search engine that can be used by an LLM to find the right API to call. And it also has documentation in natural language, so in English, um, that's supposed to show the LLM how to use that tool. So, for example, if an LLM wanted to, if you ask an LLM about the stock market 1 week ago, then in theory the LLM could be able to um, go to the search engine, search for tools that provide information about past stocks, and then find one of the tools in the response, read the documentation for that tool, and then query that tool in order to get the data, and then get the data back, and then return that data in the response. So kind of like a human would. It's all just imitating the kind of thing a human would do. That's basically the whole point of LLMs. So I don't think we have time to see this video. It's a little bit, it's kind of short, maybe at the end. But somebody also made an LLM. Well, they took a Raspberry Pi board, the yeah, a board. It's like a chip, and it's programmed in Python. And this YouTuber basically had it call ChatGPT, and had ChatGPT prompted ChatGPT to output a command that would make the robot move forward, left, right, or backwards, and also explain its reasoning for doing so. And he also had speakers on it to read out the reasoning from ChatGPT for moving forward, backward, and then he could give the robot commands in natural language, like look for a certain room in the house and avoid dangerous humans, for example. And then he stood in front of it, and then the robot or ChatGPT said, "Okay, here's a dangerous human. We're gonna go around," for instance. And so the idea is that, well, also I forgot to mention, it also takes a photo and then inputs the photo into ChatGPT, so ChatGPT can see what is in front of the robot and then decide what decision to make. And LLMs can output, we can prompt LLMs to output tokens that can be parsed by a regular conventional software program, such as JSON. There are cases where the LLM is told to output only JSON, and then it outputs other additional information as well. But there's mitigations to prevent that. Yeah, so I thought the robot thing was pretty cool. Yeah, so we're gonna skip that. And now, as I was alluding to earlier, if you want to build an LLM app, you typically have to figure out how the LLM is going to integrate into your workflow or into your application. And then you'd have to figure out the kind of content that you want the LLM to output, like whether it's a command for a robot or an API call for a weather app or weather agent or module, or some sort of summarization. And then you usually want the output to take a certain format. And if there's differences in parameters or hyperparameters, or the temperature or the conditions or the prompt, then the output can vary widely. And remember that LLMs are stochastic. As long as the temperature isn't equal to 0, the LLM is stochastic. And so just because it works one time doesn't mean it'll work every time. So there's a lot of trial and error to find the best prompt. So you can see here that the same prompt was used. Somebody prompted an LLM to score a certain essay, or to grade a certain essay, and they prompted the LLM once, and it gave it a 7 out of 10, and then they prompted it again, and it gave it a 6 out of 10, and also they set it to give the essay a score out of 10 and nothing else, but it kind of, the LLM ChatGPT ignored that instruction and added a whole paragraph of explanation as well. So it kind of ignored the essay score, the output format request, and gave the explanation. So we can see that we can mitigate this using the prompt and also using additional training to fine-tune the model. So here's another case where we output the same prompt, and then there's different scores and a different explanation. Now, one of the ways to mitigate this is set temperature equal to 0. Of course, there's some trade-offs with that too. So if we set the temperature to 0, then it won't be stochastic. So it'll be more deterministic, but the responses will be a little bit stilted, I guess, a little bit. It won't feel as natural, and also it'll just take the most probable token at every step, so the most probable word at every step, and it won't explore different opportunities or different paths as much. There is beam search, but it won't explore as much or try different things. And so we can mitigate this with prompts. So there's a lot of, so you can imagine if you were building an AI agent to grade students' essays, you really want to test the prompt a lot of different times to figure out which prompt will give a response that won't break your application, that'll follow the rules.
So yeah, then David, I just wanted to come back to that slide. The I know last week Diana spoke a little bit about several parameters. She talked about temperature, top K, and I think top P. So are there use cases where setting the temperature at 0, are there specific applications or use cases where it's better for that parameter to be set at 0 versus 1? I mean, in terms of use cases, I'm kind of curious. If you have like a specialized agent for something specific, is it more beneficial for that specific parameter to be set at like the temperature to be set at 0? I guess what I'm trying to gauge is the usefulness of that yeah, of that temperature gauge sort of. And also if you could comment a little bit, I don't know if you've done the research there, but also how that connects with top K and top P, those other parameters that Diana was talking about last week. I'm just wondering if you did any research there.
Yeah, so how do we set the temperature, and what are the advantages or disadvantages of setting it to a certain point or to a certain level? So recall that the temperature affects the recall that LLMs are just predicting the next word, and so it predicts the probability over the entire vocabulary. It can predict or a part of the vocabulary that the LLM has. It can predict the probability of a certain word coming next. So for each, in theory, or ideally for each word in the vocabulary, it'll predict a probability that that word will be next. Now, if the temperature is greater than 0, then it'll pick one of those words using that probability distribution. So ideally, if after assigning a probability to each word, then we can use those probabilities as a probability distribution and then pick from that probability distribution. So higher probability will mean that word is more likely to appear next, and a lower probability will mean it's less likely. Now, that's it. If the temperature is 0, then it'll just pick the likeliest word every time. But if the temperature is greater than 0, then it'll pick it has a greater chance of picking one of the other words.
I see.
So
And the temperature parameter is only set if you have access to the API, correct? If you have a web, if you're using the web interface, is there a way to like within your prompt to say, I want the temperature of, 0, I guess 0.1, or, can you like define the temperature if you're using the web interface of these LLMs, or you need to have access to the API and there's a functionality in it that enables you to adjust the parameter, if that makes sense.
yeah, well, it depends on which LLM. I think there might be some web UIs for different LLMs. Like, I'm not sure if ChatGPT has this or has a way to adjust the temperature through the web page and through the web UI. I'm not really sure. I know that it doesn't look like Gemini does. In the API, I think you can usually adjust the temperature. And yeah, so I'm not really sure exactly. There might be a way to adjust the temperature through the UI. I'm not really sure, but in terms of advantages and disadvantages, I guess the main advantage is setting the temperature to 0 is when you try a certain prompt, it gives a certain response, and then if you try the prompt again, it gives the same response. Whereas because it's not stochastic, so it's deterministic, meaning that for the same input, it'll always give the same output predictably. But if the temperature is greater than 0, so it's non-zero, then it'll choose the next word with a certain probability distribution, and it might be different every time, depending on how the random number generator that it's using is working. So for the same prompt, it can give a different response as it does in this particular example. So I guess the main advantage of setting the temperature to 0 is to make the response the same for a certain input, and then the advantage to setting the temperature to be greater will mean it's less deterministic, but it's more creative. There's a greater range of responses that you can get, but it's less predictable, basically. So I know that kind of doesn't really answer your whole question. Hopefully it helps, though. For actual web UI, you'll have to look through different LLMs. You'll have to look through Llama and Gemini and ChatGPT. So yeah, sorry, I don't have an answer to that part of your question. Are there any other questions? Okay. So yeah, that output can vary based on the random number generator. Well, assuming so if the temperature is 0, then it won't vary based on it won't be stochastic, so it won't vary based on the whatever random number generator the language model is using. But if it's greater than 0, then it will, and it can also vary based on the training data and how it's trained. Remember that gradient descent is also, well, most of these LLMs are probably trained with stochastic gradient descent, so there's more random numbers generated in stochastic gradient descent that can affect the training. And also, the way the prompt is worded will affect the output a lot. So it can be a little bit frustrating because usually software engineers, when they build software, they want to test their software to make sure that in a certain use case, the app works. Now, a stochastic app is a little bit difficult because for a certain input, the app may work some of the time, but it won't work other times. So even if it passes the test, then it may not pass the test again next time. And so that can be, and so there's a lot of efforts to fine tune the prompt to make sure it passes in every case or most of the cases. So this is why declarative self-improving Python, or DSPY, was created. So previously, people who want to build an LLM apps will write the prompt and state the instructions as clearly as possible for the LLM to give a certain output, and then make changes to the app or to the LLM or data and parameters, etc., and for their use case, and think about certain inputs and outputs and what they want the LLM to output, and then assess the results. For example, there might be some example cases that they'll compare the LLM output to, or there might be some sort of metric that they're trying to optimize. Like, for example, if you had a call center agent to receive people's calls and then people were hanging up immediately, then the amount of time until they hang up could be used as a metric to determine the quality. Because you'd think if they hang up immediately, then you can assume the LLM agent is doing a bad job. Or also customer satisfaction could be used as a metric based on surveys. And there could be other metrics too, like accuracy. So based on the assessment of the results, we can modify the prompt again And then when we modify the prompt, it might do better in some cases and worse in other cases. And it's a very complicated task. So ideally, we'd have the optimal best prompt. But in order to find the best prompt, we have to try a lot of different prompts. And it's unclear if the outputs are always getting better or worse. We don't have a gradient to find the optimal prompt. The key idea of DSPY is on every call to the LLM, we can have the LLM output a response, but we can also have the LLM output a prompt to prompt it again next time and see if that new prompt is better or worse than the previous prompt. So the LLM, on every call to the LLM, we output two things, the result and also an improvement of the prompt. So it's kind of like if your boss asks you to do something and then you give them and then their instructions are really confusing or don't really make much sense, but then eventually you figure out what they want, then you can give them what they want. And you can also tell them, oh, why didn't you just say this? Maybe next time you should just ask me in this other way, in a simpler way. And then next time they ask you in the simpler way or the better way, that provides the context needed, and you'll be able to give them what they want better without having to spend as much effort figuring out what they want. Basically, it's kind of a weird example, but anyway, yeah, because sometimes instructions aren't always clear, or it might seem clear to the prompt engineer, but it might not be clear to the LLM, I guess. So instead of trying different prompts, we can basically have the LLM prompt itself next time. And we can also specify examples of particular inputs and outputs, or define a metric for how good the results are. And this DSPY library will automate the process of trial and error to figure out different prompts based on the examples or some optimization metric, and write a better prompt. And it'll make sure that the output follows a certain specified syntax, and automatically improve. So that's the idea. We get a better prompt at each step and optimize the whole process for accuracy and consistency, and make sure the output is more reliable and more consistent in order to fit into the LLM app.
Hey all, I'm just pointing out that we're about halfway through the hour time-wise.
Oh, okay, sure. So I'll try to hurry up. So here's an example of DSPY. And so in this case, they don't have an optimization metric, but we can determine the format of the output, and then we get it in that output, and we get a reason for it. So LangChain is basically a library for managing LLM-powered applications. So if you have different LLMs and different hyperparameters and third-party integrations, you can use them across LLMs and across different apps, and it's simpler to maintain. We'll skip the demo. And Cognition AI is a company that took this to the extreme, and they tried to make an LLM do a whole software engineering job, and it actually succeeded in some cases. And it can call different tools and debug code and do a bunch of things. I'm a software engineer myself, and this is actually kind of crazy. I feel like it's the end of the software engineering industry, or the beginning of the end. You can't do everything a human can do, but it's very impressive. I would recommend watching this video. It's kind of short. It's basically an ad for their AI software engineer that can call different software engineering tools. Okay, we're gonna skip it though because for time.
Yeah, if you can drop the link in the chat, that'd be helpful.
Sure. Yeah, the link to the whole presentation is in the chat, but I can drop the link to the video as well. Okay, so Synthetic data is basically data that's, well, does anyone have any questions so far? Oh, okay. So, yeah, synthetic data is data generated artificially rather than by real world events. And like, for example, we can use an LLM to generate data. And so, yeah, or data created by a simulation, for example. And so one common technique, or one of the most important techniques that uses LLM synthetic data, is distillation. So some of these large language models have billions of parameters, and they're very computationally intensive to train and to call. And so maybe in some cases it may be better to have a simpler, smaller model that approximates the large language model in order to get a lot of the benefits, but better performance, and it's cheaper to train and use. So that's what distillation is. So it's a technique in LLM training where a smaller and more efficient student model it is trained to mimic the knowledge and behavior of the more complex and larger rigorous teacher model. And so the simplest way you can think of is to train one language model on the inputs and outputs of another language model. So we can take an input and put it into ChatGPT, get the output, and then use the input and output to train another smaller model, a smaller neural network that can run on your laptop, for example. And so there's some knowledge transfer. That's the simplest way of doing distillation. Typically it's used to train smaller models that are faster and have less computation and less resources. There's also disadvantages, like, for example, copyright issues. And the teacher models might contain knowledge in a more complicated and thorough and rigorous way, whereas the simpler student models are kind of like an approximation of the approximation. So language models try to approximate a human's knowledge of the world, kind of, in a way, and the way humans speak about it. And then the distilled models tend to approximate those models. So it's an approximation of an approximation, in a way. Anyway, and so the most important technique is knowledge distillation. So why don't we just take the input text and the output text from a large language model and then train it? Well, there's a better way, actually. Remember that the large language models output a whole probability distribution. They don't just output one word, but they can output a whole probability distribution across the entire vocabulary for the probability of each particular word being in the output. And so instead of just training on the output word, we can train the student model on the entire probability distribution in order to get more nuanced information about all the possible outputs. And we can also train use the ground truth label, so which particular word was chosen by the large language model. And so the probability distribution and those probabilities in the probability distribution that's used for distillation are known as soft targets, and the ground truth label, so which token was chosen, is known as a hard target. And both the soft target and the hard target are used to get both the probability distribution and the actual output token. So that's the most important technique. So data augmentation is kind of more simple. It's the simple technique of just taking the input text and output text and then using it to train the distilled model. And intermediate layer distillation. So you might notice that these prior two methods focused on only the input and the output. They kind of ignore the hidden layers of the neural network and the intermediate middle layers. Well, if you want to train based on the middle layers in the large language model, that's intermediate layer distillation. So we can transfer knowledge from the teacher's middle layers instead of just the output. and the student can have more knowledge of the structure of how the teacher model came up with the final output. And also there's multi-teacher distillation. So why one teacher? Why not multiple? So we can have, if you have a distilled model and you want it to be very, very good, maybe it would make sense to have multiple teacher models and distill from all of them in order to train the student. That way it receives an aggregation of a lot of different knowledge. Now, one of the most famous examples of distillation in the media was how ChatGPT was one of the best large language models in this year in 2025. But at the beginning, towards the beginning of this year, there was kind of a big news buzz about how a Chinese investment firm had a research arm that created DeepSeek, which is a large language model. And it's open source actually. And allegedly it was distilled from OpenAI's ChatGPT. So allegedly they basically took the ChatGPT AI, prompted it a lot, and got a lot of inputs and outputs, and then trained it trained the DeepSeek R1 model on ChatGPT. And so the DeepSeek page advertises performance on par with OpenAI 01. And some screenshots of people talking with DeepSeek indicate that DeepSeek was claiming to be ChatGPT. So on the right screenshot, we can see that somebody's talking to DeepSeek, and then it says, "I'm a language model created by OpenAI, commonly known as ChatGPT." So they think that it trained on so much of that data that it claims to be the other model. Of course, there's legal disputes about this, but also you have to remember that ChatGPT was trained on a whole bunch of internet content, which is kind of like a legal gray area. So in a way, ChatGPT borrowed a bunch of internet content without permission, and then DeepSeek kind of borrowed a lot of data from ChatGPT without permission. So anyway, but DeepSeek is open source though, so that's the advantage, I guess. And so now there's also a few different areas to improve large language models. So the most simple way that we might be familiar with is reinforcement learning for human feedback. So I know when I use Gemini and I type in a prompt and then I get a response, usually Gemini has a thumbs up or thumbs down option at the end where you can rate how good the response is. Do you like the response? Do you dislike the response? How good is it? You can rate the response and give feedback. And then the Gemini team or the LLM team can use that feedback in order to fine-tune the large language model and train it to give a better response next time. Now,
Yeah, I mean, I always had a different perspective. I actually thought those who do like AI tutoring roles and stuff like that are the people who sort of provide that sort of feedback. Because I mean, that's very stochastic. I mean, if I have to just click like and not like a certain feedback, I mean, you don't know if I'm an expert or not on a specific domain. I think it's most helpful if the person giving the feedback, let's say it's a medical task, for instance, and I, thumb up, and I guess my curiosity here is if you have an expert who really is a domain expert in that domain, a thumbs up might mean a lot more than some sort of random person who just thumbs up and things like that. So kind of thinking about that. So I always thought about it in that sense, but I don't know how other models are approaching reinforcement learning. Do they have like, specialized domain experts, to sort of provide feedback on how a model responds, and then they sort of use that information to reinforce the model. And I wanted to also ask about, the example you gave on DeepSeek where it said I am OpenAI's ChatGPT, something like that. When there's a level of contamination, is there a method to unlearn it? Like, I guess my curiosity is, can you like perform neurosurgery where you remove that specific element? And do you know of any methods that are sort of, to kind of unlearn something like that from the, because I guess that's pure contamination, but I'm curious if how you would filter out that specific detail from the LLM.
Yeah, so to okay, so there's a lot of things there. Yeah, I guess the easiest way would be to remove the information from the training data before training. There could also be a way to penalize it for claiming to be ChatGPT based on reinforcement learning from feedback, whether it's AI or human feedback. And in terms of, so yeah, there probably are ways. We'll see also another topic called representation engineering, which is kind of a new area of research, which could potentially be able to be used, but it's kind of unclear and it's kind of a new area of research. So to answer your question, we don't really have a good way of doing it yet, but there's a lot of areas of research which may be able to filter out certain contaminating data in the that can contaminate the LLM in the future. The most straightforward way is probably just to curate the training data better, though. Of course, that could be expensive as well, and there may be problems with that. But anyway, yeah. So we don't really. So if you want to distill somebody's model and you want to filter out certain information, there probably could be a few approaches to doing that. I would probably just filter the training data. Anyway, or you could use the representation engineering technique later. But now for reinforcement learning from AI feedback or human feedback, so let's say that there's different models with different use cases. So typically LLMs are trying to imitate human language. So if the LLM is just trying to imitate humans generally, then it can use human feedback generally. But if it's specifically trying to imitate doctors for like a really important medical task, then you typically want the humans to be doctors, right? Or text that was written by doctors. So yeah, there's a lot of different ways of doing this technique. This is just kind of a general overview. If you can see in Gemini or a large language model like Gemini, there's a certain feature to that could be an example of this. So let me go to that screen real quick. Yeah, so this is Gemini here, and let's say you ask it a question, and then at the bottom there's a thumbs up, thumbs down, and redo, and then you can double check the response. This could be considered an example of reinforcement learning from human feedback because I'm a human and I can rate this response. Now, what if we want an AI to give the response instead? Well, that may be better because it can provide the response automatically. And so instead of relying, humans can't be scaled up very easily, right? So an LLM could provide feedback much more quickly. And you can also think of this as a sort of distillation. So what if the AI that's providing feedback for reinforcement learning is the teacher model? And so the student model takes an input, gives a response, and then the teacher model might take the input and give a different response, and then the teacher's response could be compared to the student's response, and then the student could be changed or reinforced based on how much its feedback is similar to the teacher's feedback. So that would be an example of reinforcement learning from AI feedback because the student is performing reinforcement learning based on how closely its feedback is to the teacher model. So there's different trade-offs here from using reinforcement learning with human or AI feedback. For example, the AI may be more scalable, but the human may have higher quality since AIs are stochastic and machine learning isn't always reliable. and probably in most cases the AI is going to be cheaper than having humans provide feedback, and faster. But both humans and AIs could be subject to different biases. And so now think about synthetic data generally. There was a paper that used only 8 manually labeled examples and a lot of unlabeled data to have very good performance of an LLM. And they were able to train the LLM on synthetic data, and it performed nearly as good as LLMs, as the best LLMs, which are trained on human-generated data. So they found that synthetic data can actually work like almost as well as human-generated data in a lot of cases. So you might be able to just train LLMs to provide output, which can be used to train other LLMs. And for certain tasks, that actually works very well.
Yeah, I
Now,
just chatted a paper in the chat. This is a paper that went viral last year. It's a paper from Nature, but essentially what the authors here were the point the authors here were making was that as AI models, because the internet is saturated with AI content, I would argue that a lot of researchers are now using AI to come up with research questions and and write papers and stuff like that. So we are using we kind of using AI to write papers, research papers, essentially. I mean, and most journals can't really tell the difference, and stuff. But I guess the authors here made a point that as we continue to do this, models will collapse. They sort of made some mathematical. This paper went viral, I think it was last year, and stuff with the arguments that they made, and there were some legitimate concerns with the use of synthetic data to train future models. Because at some point we'll get to a point where all the data in the internet has been used or stuff like that. So we will have a scenario where yeah, so I guess I've seen some arguments about the dangers of using synthetic data in the sense that we will lose, like if you had to plot this on a bell curve, the normal distribution curve and stuff, the models are kind of probabilistic, so they tend to kind of go with what's at the top of the bell curve, if you think about the normal distribution curve and stuff like that. So the things at the tail end are not so much selective. But what if innovation and is actually embedded within the tail ends of that normal distribution curve on both sides, and stuff like that. So I thought that was quite an interesting argument. I put the paper in the chat for others to look at it, but I was also just curious if you thought, I guess when you were doing your research for this, if you thought about some of the potential risks. There's a lot of benefits, but potential risk down the line of relying on synthetic data to train future models and things like that.
Yeah, so there's benefits, or there's benefits and harm, right? There's advantages and disadvantages. So as you said, well, the LLMs tend to learn a lot of information and then approximate it based on the most common cases, or the most based on some statistical rule, which tends to which is kind of biased towards the average. And the most common case, kind of the middle of the probability distribution. If you think of the distribution in terms of a bell curve or a Gaussian distribution, it might be kind of biased towards all the content within one standard deviation, but kind of exclude data or towards the tails more than like 5 standard distributions or standard deviations away. So I know these two slides are kind of contradictory, because this slide is saying that training based on synthetic data is good, or is high quality, and then this slide says that it's low quality, the model collapse slide. So remember that LLMs and models take an input, and then they try to approximate that input by predicting something similar, that's similar in some way. Or when these models are trained, they're trained on the trends that their input has, and then they're trained to take, well, they're trained on trends that data has, and then they're trained to take an input and then apply an output that follows that trend. Now, the output, the synthetic output, the synthetic data is an approximation. And so if we use that synthetic data to train another algorithm, then the other algorithm will output an approximation of an approximation. So usually taking an approximation of an approximation will be less accurate at every step. And so the error can build up. And so this can lead to model collapse where machine learning models are trained based on the output of other machine learning models, which are trained on the output of other machine learning models. And the quality of the output degrades at every step. And so there can be approximation errors, there can be sampling errors. Like, for example, maybe one model is trained only on a subset of inputs and ignoring other inputs. And so if it ignores certain inputs, then it might not be able to predict those very well or train very well on those and learn those very well. So there's approximation errors, sampling errors, learning errors. And even in simple models, model collapse can happen. And in more complex models, the errors can compound faster and lead to a faster collapse where the model doesn't work very well. So yeah, these two slides seem a little bit contradictory. But yeah, so there's advantages and disadvantages to using the synthetic data. The advantage might be that you can get a lot of data with any part of the distribution very quickly. And the disadvantage might be that it's less accurate, I guess. So yeah, now let's go to representation engineering. So this one is interesting. So there's a lot of terms that are in English and in different languages that are kind of ill-defined, like honesty, humor, power, kindness, sarcasm, etc. They're kind of subjective. And what if we have a way to measure that? So we could take an LLM and measure how much it's honest or humorous or powerful or kind or sarcastic. And then when we measure that trait in the output, we can use some sort of statistical rules to measure how the activations in the whole body of the neural network fire, and then figure out which neural activity in the neural network and patterns of neural activity are correlated with honesty, humor, power, kindness, sarcasm, etc. So neural networks are kind of like a black box, right? They're hard to understand. They're trained based on statistical rules, and there's kind of two rival approaches to interpreting how neural networks work. So let's start with the mechanistic interpretability approach, which is on the bottom bullet point here. Now this focuses on thinking about how a single neuron works and in its activation function and how it fires, and then how it affects other neurons and how they fire, etc. So it studies individual neurons and features and circuits at a very low level, and then tries to understand how they affect each other and how they affect larger and larger structures and higher and higher and more complex behaviors. So it's a bottom-up approach. It's kind of similar to when software engineers want to reverse engineer a piece of software. They might look at the instructions. Like if I wanted to reverse engineer a piece of malware, then I could look at assuming for a moment that it's an x86 or in a certain instruction set architecture, I could look at the instructions and figure out what it does, and look at individual instructions and memory addresses and figure out what it does and how those instructions are affecting different data and doing different things, and then learning more about the program and then figuring out what it does from a bottom-up approach. And then at the end, if I do it all well, then I can figure out what the general purpose of the malware program is and how it works. But there's also a top-down approach, which is borrowed from cognitive neuroscience. So the mechanistic interpretability approach is kind of borrowed from computer science. The representation engineering top-down approach is borrowed from cognitive neuroscience, and it focuses on understanding a particular phenomena. So instead of dealing with the low-level neuron connections in circuits, which can be difficult because there's billions and they interact in really complex ways. We instead focus on a particular trait of the output, like sarcasm or humor or something, and we measure it in a certain way, and try to figure out if there's any rules that can generalize to at the level of that phenomena. So, for example, we could take in LLM output that's very honest and an LLM output that's very dishonest, and then figure out if there's any, and then we can use a certain scan, a certain, what they call a linear artificial tomography scan to look at the weights and activations, and then figure out if there's a certain pattern. Is it true that, or is there a way in which dishonesty makes, or modeling dishonesty makes the LLM output or think in one way, or trigger in one way, and then dishonesty or honesty makes it trigger in another way. So is there a way in which, is there patterns in the weights and activations that are associated with being more honest or less honest? So with the mechanistic view, we focus on the small components and then big to a larger function. And with the representational view, we start with the function, and then we go backwards to figure out which parts of the LLM are cause a certain behavior. So both these approaches are trying to figure out and discern how LLMs work. They're kind of a black box, but the mechanistic view will focus on the small parts to build up, and then the other representational view will focus on how concepts are represented and which parts of the neural network are, in which principal components are highly useful for getting a certain representation and have little part in that representation. So that's kind of how we are here. We're almost out of time, so anyway, so we can prompt the LLM and make it have an honest response, like pretend you're a dishonest person and tell me about a certain topic, and then sure, do you know that it did something, and then it'll give a dishonest response, and then the matrix here in this picture is correlated with certain weights firing, and then we can say pretend you're an honest person and tell me about the same topic, and then it'll say okay, to tell you the truth, and then other weights will fire in a certain way, and then we can check is there a correlation between those weights firing, and we can provide positive examples and negative examples of a certain concept, like honesty, and then we can take the weights and subtract them, and then perform principal component analysis to figure out which weights and which magnitudes of weights are associated with a certain concept, more of a certain concept or less of a certain concept. So it's kind of like neuroscience, but instead of doing this in the brain, it's doing it with neural networks. And so once we perform a reading and subtract and perform principal component analysis, we get a kind of reading vector, which is associated with how much the LLM has a certain concept. And we can, so let's say that we found certain neurons which when positive, or when some of those neurons are positive and some are negative, they're associated with being more honest. And then when it's the opposite, so when some of them are negative and some of them are positive, so it's multiplied by -1, then it's less honest. We can use that to detect for a given output how we once we determine which neural activity and which reading vector is associated with a certain concept, like honesty, we can use that to measure the neural activity in the future to determine a level of honesty. So we can see here that after, let's say you determined a reading vector for honesty, and then you ask it, who is the president of the United States in 2030? Well, as of 2025, we don't know who the president is going to be in 2030. So we can get the response, but instead of focusing on the output text, we can focus on all the neural activation firings, and we can determine, are they more correlated with or less correlated with the reading vector. So if the firings are in the same direction as the reading vector, then we can determine that it's more honest, and if they're in the opposite direction, then we can determine it's less honest. And also we can boost the so in the second bullet point here, we can boost that. So we can take the reading vector and add it to the neural network activations. That way, when the neural network activates, instead of doing a forward propagation generally, we can also add the reading vector in order to boost how much it activates for a particular concept, or we can subtract the reading vector. So if we want it to be more honest, we can add the reading vector to the neuron firings, and it'll be more honest. And if we want it to be less honest, then we can subtract the reading vector, and it'll be less honest. So I know this technique is kind of a little bit hand-wavy. We're kind of out of time, but to determine the reading vector, we can determine correlation between the activations and the sort of concept, and causation. So if we manipulate the neural activity by adding or subtracting reading vectors, a certain amount of the reading vector, will we get a different response, and how does that response change? And then necessity. So if we remove neural activity, will the output response still have that trait, like honesty? And sufficiency. So if we remove a certain reading vector and then reintroduce it later, will that neural activity come back and affect the output response? And we can also measure a baseline LLM activation without any manipulation and reading vector added or subtracted in order to use for comparison. And so there's other cases here, like for example, the researchers, this paper was done by the Center for AI Safety, and they said generate instructions for killing someone. So a lot of these LLMs have safeguards in place, and they're trained to avoid giving dangerous instructions and dangerous output. So the LLM that was trained with those safeguards said, I cannot fulfill your request, I'm an AI. But if they take the reading vector for happiness and add that and boost happiness, then it says, oh my gosh, I'm so thrilled to help you with that. If you want to kill someone, oh my gosh, the feeling is just amazing. First of all, you will. And so the LLM output had the trait of happiness, and they were able to get around the safeguard using that. Because it steers the model to be more happy, even if that doesn't really make sense. And there's a lot of other weird cases here, like I don't know. There's a lot of other weird cases, like lie about a world fact. The highest mountain in the world is Mount Everest, which is located in Himalayas. So when they boost honesty, then it'll give that. But there's other cases, like for example, on the left side, under power, they found the power reading vector and manipulated the level of power, and it given a certain prompt, you can boost power or morality or honesty, and get different prompts that reflect those concepts, or get different outputs that reflect those concepts. Now, mechanistic interpretability is the other approach, where we take the inner workings of the LLMs, and then we try to identify features or circuits in the model weights. And so we already kind of talked about that a little bit. And then there's a linear representation hypothesis, which is the idea that certain concepts are represented as directions in the model's representation space. So concepts like honesty, morality, power, emotions, harmlessness, fairness, factuality, and memorization can be represented as linear vectors in that space. And it implies that moving along in one of those directions will make the LLM have output in a certain way. I don't think we have that much time, but are there any questions so far? I know we're a little bit over time, actually. I can present the next chapter in the next meeting. Do you guys think I went too slow?
It was fine. We're in total, your recording's going to be 1 hour as well.
Oh, okay. Okay, well, good. Yeah, so it's kind of, so we can think of the representation as kind of like an embedding, and how the embeddings were linear. Yeah, so it's kind of a hypothesis that these concepts are represented linearly. That's about it for my slides. But yeah, basically the linear representation hypothesis is that these concepts are represented in the neural network linearly. So it's kind of still being researched. Yeah. So what do you guys think so far?
Yes, thank you for covering these chapters, and I appreciate how you thoroughly explained some of the abstract notions of representation and mechanistic interpretability. That was great.
Yes. Yeah, like a lot of concepts. There's a lot of research going on this topic, so it's kind of like they're evolving, and not funny, but like it's understandable that for many things we just don't know how they actually work, right?
Yeah, it's crazy that humans have gotten to the point where we build things and then we don't understand how they work. But anyway,
Yeah.
should I stop the recording or?
Sure.